YouTube, happy weekend. Today we're going to look at the 90 amp Harbor Freight welder. There's a lot of them out there. That one's mine. Did a few modifications to it. Runs a whole lot better. We're going to take you through it. So overall, I like this welder a lot. One of the most important things you can do right off the bat, very inexpensively, put your ground clamp on it that does not do a bad job. Put your ground clamp on that does a good job. This is a Hobart. I think it cost me $8 or $10 off Amazon. One of the things you look for in a ground clamp is that where the lead comes in, goes through, and connects to the other side. This one does not. I had a ground strap laying around for, like automotive work. I kind of made my own, and you know what? Huge instant performance increase. If you do nothing else with this welder, throw a $10 ground clamp on it, and you will get better beads with a little bit less spatter right away. It's not huge. It won't turn it into an amazing machine, but it is the quickest, cheapest thing you can do. What I've done to this is convert it to DC. You can see something there that doesn't belong. So I'm going to take it apart real fast and show you what is happening inside. I am just a hobbyist. I'm not building anything where anybody could really get hurt. Nobody's life depends on anything I weld. Don't claim to be a welder. Actually, my background is more cabinetry, so it's kind of a fun thing for me to be into. The whole reason I'm fooling around with this is to make fun stuff, like what's going to be a smoker one day. There's the summer project preview. We'll try to take a video of it. I'm not very good at YouTubing either, so we'll see what happens. So we'll get into the guy here and we'll have a look and show you how I convert it to DC. It is definitely a much better welder on DC. I had it for about a year before I did the DC conversion on it. If you're intimidated to do it, to make it a DC welder, there is a lot of good tutorials out there. I will not claim, for this one to be a step-by-step. This is more of I did it, and here's where everything can fit. And I'll show you a couple of the welds done with it and how much better it can look. So if you want a step-by-step tutorial, there's a handful out there that are better, by all means. This is just to show you the average guy can really do it. What you want to know is how to solder. If you can solder, it's going to be a much easier time for you. If you don't know how to solder, you can learn. You know what? Maybe I'll make a video about that. Alright, here is inside of the Beast. Beast term used loosely. As you can see, we have the super classy fan duct happening. We are coffee drinkers because we have children. Lots and lots of hot snot holding it on there. And you know what? It hasn't come off yet. I haven't put this thing to absolute task. I haven't actually gone to thermal overload yet. I have before, but I haven't done it after the modifications. But I don't think it'll melt back there. So as far as components to do a DC conversion, you're going to want to get a bridge rectifier, at least 100 amps. I hid mine up here. This is in the back, right above the fan. It's helpful to know you could move that fan down probably about 3/8 or nearly half an inch and still clear the bottom. I would definitely recommend doing that. It'll give you just enough room. I also recommend ducting it in. Before I ducted my fan in, I never felt a breeze out of the louvered vents. And I absolutely do now. The thermistor, the thermal overload, is right here on the other side of the transformer, and so it's literally telling you when that transformer is too hot. So the more air you can move through the case, the better. Without a duct, you're basically tumbling hot air inside the case. That's really easy. There's nothing hard about that. So as far as components, like I said, we got the 100 amp rectifier. I'll throw a little light on it right there. Then you've got a couple of capacitors. Capacitors are kind of expensive if you have to buy them. This is where I hid mine, right here. This is the right side of the unit. There's enough room in there if you're kind of careful with them. I got these capacitors from a power supply that went up. The bridge rectifier in it died. It was a radio power supply, like a 25 or 30 amp unit. Really, technically, you would love to have twice this amount of capacitance. And if you've researched this product, you'll also notice I did not do a large wound inductor on mine. I didn't have a good core laying around the garage, and this was all about what was laying around the garage. The only money I have in this is $12 for that rectifier. So even though this is probably about half of the capacitance you would really want, it still makes a huge improvement. There's far less splatter on the welds. And I'll explain that in a few minutes why you're doing all this. I'll make a little drawing on a steno pad. If you do this, you also do want to do this bleed resistor. It gets tied in parallel to the caps, plus and minus. I went with a 10 watt 100 ohm. It does not get warm. And 100 ohm is a really nice value. It's not low enough that it robs welding power. It's not high enough impedance or resistance that it takes so long to discharge. Within a couple seconds, you have nothing left on the gun, or maybe a really light spark, and in 5 seconds there's nothing there. So don't forget that bleed resistor. So the way you want to do it, again, there's better tutorials than mine, but your power transformer has two outputs on it. You can tell they're the outputs because you have a red and a black. They are not DC, they're AC, but that's just the wire coloring they used in this welder. That runs back to the board. It's a lower voltage AC from that transformer. It runs the wire drive up on top, and the circuitry that controls that, and the speed control, etc. So the easiest thing to do is not fool around with the connections, between there and that hard wire coming out of the transformer. What I did was I interrupted the ground output, and I interrupted and I cut it right here where it heads up. That's where it heads up into the wire feed. That's your lead. Remember, if you are doing flux core, you want to be DC electrode negative. I put a little piece of red tape here just to remind me that is actually the positive DC. Once it's connected, it don't matter. You're not going to change it. So that's where I severed the ground and the lead wire after the connection of the transformer to the circuit board. So you're basically running the output of the transformer to the AC in of the rectifier. The DC out of the rectifier just connects up to the work leads themselves, positive and negative done correctly, positive to the ground clamp and negative up to the wire feed for the gun. And then what you do is you tie the caps in parallel to that, and the capacitors are going to be positive and negative labeled, positive to positive, negative to negative. And again, I'll draw that out here in a minute for you. But I can tell you the quality of the welds are far, far better. This is examples of me trying to work the settings out. Those are not the pretty welds. This is, and these are a couple welds after the settings were dialed in. I had to run my wire speed quite a bit less after doing the DC conversion. This spatter really all came from doing these ugly welds with too much wire speed. I used to run the wire feed all the way up, or always above 6 or 7 towards 8, very commonly on the max voltage setting. So I just brought it to this and did that, and it was severing the wire. It was, the arc was so strong, it was melting the wire before it really had a chance to get into the metal. It was almost like spray arc or something. And of course it was doing a bad job because it probably hasn't got the guts for that. So I brought the wire speed down to, I don't know, 3 or 4. And with just a little bit of weave action, it was getting very reasonable welds. They're flat. They lay in the metal nicely. Again, those are me working out the settings. There's a decent one right there once the settings were dialed in. And again, there's almost no splatter that came from this. This was all here ahead of that. So this DC conversion is definitely worth doing. Let me draw out for you on a piece of paper what's happening electrically. All right, everybody. I am by no means an expert. Shocked myself enough times to have some idea of how electricity works. None of it's actually that complicated. Put your thinking caps on with me and follow along. 120 volts comes in the main plug. Simple enough. That comes in right there, goes to the on-off switch. You have the big transformer. This is what it looks like on paper. Okay, 120 volts coming in right there. That's no polarity, that's literally going up and down. That's AC current. What's AC current? Let's draw AC current out for you. AC current varies in this country 60 times a second. You have a 0 line, plus 120, minus 120. Like this is AC current. Right there is 60 hertz. That means 60 times a second you have a wave height roll through. Look at that, you can't even see it. There you go. 120, 120. This is a sine wave, sinusoidal wave. 120 volts positive, 120 volts negative. That means it flip-flops, and it does at 60 hertz, which is the time period, which is the frequency. That means it is wave height, peak to peak, 60 times a second. And that's how often that flips polarity. Now DC, if you know in your car, you have a positive and a negative. That's what we're looking for in the output of this welder. When you buy the welder from the factory, you get AC on the output, but a lower voltage because it goes through the transformer. So you're getting whatever that transformer puts out AC. I think it was around 35 volts AC. That AC current is why this machine is so puts so much spatter out on your work. This AC current is going in the work and out of the work, and in the work and out of the work, and it sends spurts of metal out every time it does that. And so it's also a lot of wasted energy. You don't get as much penetration. I had a very hard time with this machine making welds that would wet in and lay flat, so to speak, in a joint. They all tended to want to sit proud, and it was very difficult to get it to wet in and penetrate fully. Much better after the DC conversion. DC, okay, that's AC. DC, I'm going to just draw a line here to divide that. DC, we're going to go plus, and then we're going to talk about the output of the transformer, because that's where the rectifier is. So our circuit is power comes into the welder, goes to the transformer. We interrupt that after the transformer. It just would go right out to the gun and the clamp. What we've done is interrupted that, sent that to the bridge rectifier. So the output of the transformer, 35 volts AC, goes to the bridge rectifier and comes out looking exactly like this. You get the same 60 hertz, but what it's doing is flipping, so the time periods are the same. It is flipping this negative. You know what? That's hard to read on one piece of paper. Let's draw DC on a fresh sheet. Plus, minus. It is flipping. Instead of going down under and coming back over, it is taking what was under, and the rectifier, it's got 4 diodes in it in the bridge configuration, is throwing it up on top. So you have the same 60 hertz, period, same frequency, but instead of it dropping down to negative, they're all above. They're all in the same polarity now. That is what a bridge rectifier does for you. My buddy and I worked on, my brother-in-law actually did his machine with just a bridge rectifier 3 or 4 years ago now, and that alone is a decent improvement. If you don't have capacitors around, don't wait. For 10 or 15 bucks you can get a rectifier, and it made this welder a lot better with just that change alone. Now what the capacitors do for you is they charge up. Now we're going to go back to the schematic here in a second, but the capacitors on the output of the rectifier charge up, 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 up at the peak of the cycle. That's the peak right there. They discharge on the way to the next peak. So instead of the voltage going to peak, say that's 35 volts DC, roundabout, and then driving way down to nothing, and then ramping back up, the capacitor keeps it up at a higher average. Now the capacitors that I have two 10,000 UF. I have them in parallel, so that's double. I'm running 20,000 UF on this unit, and it is because it's what I had. I am too cheap to just run out and buy, capacitors, especially large ones, can be a little bit expensive. Like I said before, I salvaged them out of a power supply. They work great, there's nothing wrong with them. I would love to have twice that, I think 40 or 50 even microfarads would be an amazing, and that's UF. I think that would be an awesome amount of filtration for this, because what that's doing is the more capacitance you have, so I've got two 10,000, so I've got 20, the more you have, the closer this stays to the peak. If you have too little of capacitance, if you're too small, it'll discharge quickly. It's literally how much charge that can be held. So if you put a 5,000 microfarad capacitor on this as a conversion, it's probably, I don't know this, I don't have a scope, but it's probably going to look like this. Is it doing something? Yeah. Would you notice it on your welds? I don't know, probably not. Minute of garage precision, whatever. So the more capacitance you can get, the better. Capacitors are expensive. Try to salvage them. They need to have a voltage rating in excess of what the output of that transformer is. These capacitors are rated at 45 volts. Wouldn't have minded them being a little bit larger than that. They probably won't burn up. They'll be fine, especially low duty cycle work. Okay, now let's look at the schematic. You have 120 volts coming into the machine. It goes through the transformer. On the output of the transformer, you still have an AC sine wave, up and down, 35 volts roughly. And it goes into the rectifier. That's not how you draw one schematically, but it works. See the R? It's a rectifier. From the output of the rectifier, you have a plus. How can I not shadow that? You have a plus and a minus. Plus, minus. That is positive and negative. This is a symbol for capacitor. Your capacitor is to be parallel. I'm going to hold real still here, and you can screenshot this if you want. Your capacitors are to be parallel on the output of the rectifier. Meaning, if you think about the rectifier going straight out, positive goes to the clamp, negative goes to the gun. You are literally connecting your capacitor or your capacitor bank, if you have more than two, in parallel with that. Now, if you're putting two capacitors together, you join their positive to their positive, their negative to their negative together, and then to the work leads coming out of the rectifier. Now, the bleed resistor is very important. As I stated before when we were inside the unit, if you don't have a bleed resistor here, these capacitors will charge up on a peak. Now let's say you stop welding. You're done welding. They're going to stay charged, and they're going to sit there charged up with 35 some odd volts DC. It's not likely to kill you or stop your heart. I wouldn't go licking it. But that being said, as soon as it touches your work or whatever is grounded in your system, connected to your ground clamp, you're going to get a great spark. It's going to scare you. It's going to shock you. It's going to surprise you, I mean to say. It's not a fun experience. You don't want to do that. It's sketchy. So when you connect a resistor, I used 100 ohm, 10 watt, it's just going to bleed that capacitor on, pretend there's paper there, on down to nothing safely over the course of a couple seconds. Hopefully that makes sense. You're going to connect again that resistor in parallel with your capacitors. Now, let's do something in the real world. Let's watch a meter while I weld. I'll just throw a quick ugly, I'll just spurt some on some metal, and we'll put the camera on the actual multimeter here while I weld, and we'll see what that voltage looks like, and we'll watch the resistor bleed the capacitor down. Something else when it comes to the rectifier, again, the rectifier is mounted right above the coffee cup, right there. You want to have some kind of heat sink on that. Wherever you mount it on your case, it needs to be heat sinked. This is borderline a little small of a heat sink probably. It's about 1 inch deep. It's got a fan on it, which I found and promptly zip tied to it. The more zip ties the better, right? Right. That rectifier gets hot. I've got 100 amp on this unit. It's a 90 amp welder. That's actually cutting it kind of close in electrical terms. Margin is better for duty cycle. That being said, with the heatsink and the fan, that should buy some time on it. If you really want to try to go far with this, it really is no reason in the world you could not do a 150 or 200 amp rectifier. That just means it's not going to sweat as hard. It's like a really buff guy at the gym versus me. Alright, so your capacitors have polarity. Mine are labeled, they're labeled in different ways. Some of them had red lacquer on a terminal, some of them are labeled on the side of the case. I'm going to hook this up negative to the negative side of the capacitor, positive to the positive side of the capacitor. My meter is in DC, ranged to 200 volts. Because this is not an auto ranging meter, because it is a cheap one. I found it to be accurate enough though for this. It'll do just fine. So what we're going to do is, without any welding at all, we're going to show you what it looks like to charge the caps and bleed them out. So I've got the machine on maximum voltage, maximum power, maximum voltage. We're just going to send some wire out. Now I want you to watch the meter. Okay, we're going to turn the machine on and then try it again. Watch the meter. 36 volts. Now, see it discharging. That is that bleed resistor taking it to zero. Now, that took, 5 or 7 seconds or 8, 9 seconds to come all the way down. We're not really worried about getting all the way down. What we're trying to do is just to get it down low enough that the arc isn't terrifying. So that's the basic premise. Just for reference, kicks and giggles, if you want to see it, we'll throw the voltage to low. 28.7, high. There it is. Alright. I'll throw my hood on real quick and we will actually put a little bit of bead down so you can watch the meter as that's happening. And you can see it discharging well. Just brushed off the flux. So the little bit of BBs that are right there, I ain't touching it, sorry y'all, that are right there, those are new. Those actually came with this weld. But you can see, if you own this machine, they're quite a bit smaller than what you had. It's not the world's greatest bead at all. It's a little bit lumpy and irregular there in the middle. I was kind of standing off angle and I'm going to make a bunch of excuses about that, and that's fine. But as you can see, it is quite a bit flatter than what, well, at least what I was getting out of the machine. It's a nice flat weld, good heat on the side of the metals. The bottom of it's going to show some heat marks. So definitely worth doing, definitely worth converting this machine to DC. Take your time, scrounge some components. It can be done with a rectifier, find some capacitors. If you throw capacitors in it, absolutely do a bleed resistor. Definitely worth upgrading this clamp. That's a $10 thing. You know, it's the kind of thing where this is a $100 machine, maybe even $50 if you find one used, because people do sell them because they get frustrated with them. So you're not wanting to throw another $50 or $60, say, into components. That just does not make any sense. Why would you do that? So that's kind of why I look at it as a scrounge operation. That's that. Hobbies are fun, weekends are better. Have a good weekend. Bonus, the astute observer with the keen eye will notice that the location of this heat sink prevents this from opening all the way. I noticed that and I don't really care. I could have cut all those off. It's just like a powdered aluminum or something, and I didn't care enough to bother because that is very easy to pop these two screws off right there, lift that whole lid off when I have to change a wire. Which, if you weld a lot, it's probably kind of frequently because it's a tiny little spool, but hey, small price for progress.